When the Second World War erupted in 1939, artillery was already considered the king of battle, but its form and function were still heavily influenced by First World War practices. Artillery in World War I had relied on static positions, slow, moving guns, and heavy barrages that devastated landscapes, but often failed to achieve decisive breakthroughs. By contrast, World War II presented new challenges and opportunities that demanded rapid modernization. The nature of mobile warfare, blitzkrieg tactics, and combined arms coordination forced militaries to rethink how artillery should be designed, deployed, and used. As a result, a host of innovations emerged during the conflict, many of which continue to shape modern artillery doctrine and technology today. Among the most influential were self-propelled artillery systems, advanced fire control methods, rocket artillery, proximity fuses, and radar-based targeting systems. These breakthroughs did not just improve efficiency, but completely redefined artillery's role on the battlefield. Instead of being confined to defensive bombardments, artillery became a dynamic force, supporting armored advances, repelling enemy assaults, and engaging in long-range precision strikes. The war thus acted as a catalyst for transforming artillery into a modern weapon system that combined mobility, accuracy, and devastating firepower. Before World War II, most artillery pieces were towed by trucks, horses, or tracked vehicles, making them slow to reposition. This created a serious problem in the new era of rapid mechanized warfare. Armies that relied only on traditional towed guns often found themselves unable to keep up with fast-moving tanks or respond quickly to enemy maneuvers. The solution came in the form of self-propelled artillery, a revolutionary idea that placed large, caliber guns directly onto armored or tracked vehicles. Germany pioneered this with vehicles like the Wesp and Hummel, while the United States produced the M7 Priest and M12 gun motor carriage. These mobile artillery systems provided several advantages. They could follow armored columns, deliver immediate support, and then relocate to avoid counter-battery fire. This mobility significantly increased survivability and tactical flexibility. Furthermore, self-propelled artillery allowed commanders to integrate fire support directly into armored formations, ensuring continuous firepower during offensive operations. The concept of combining armor protection, heavy firepower, and maneuverability was so effective that it became a cornerstone of modern artillery design. Today's howitzers, such as the M109 Paladin or Russia's 2S-19 Mister, are direct descendants of these wartime innovations, highlighting their enduring impact on modern warfare. One of the most critical lessons of World War II was that mobility could determine victory or defeat. Static artillery, no matter how powerful, could be outflanked or bypassed by mechanized forces. Blitzkrieg warfare, demonstrated effectively by the German Wehrmacht, relied on speed and shock. To counter this, artillery had to be just as mobile as tanks and infantry. Self-propelled artillery became the answer, but mobility extended beyond just mounting guns on vehicles. Towed artillery pieces also underwent design changes to make them lighter, easier to transport, and quicker to set up. The British 25-pounder, for instance, was designed with versatility in mind, capable of both direct and indirect fire, and easily repositioned in battle. The Soviet Union also mastered the use of mobile artillery in its vast territories, where the ability to move guns across rough terrain was vital. By the end of the war, it was clear that mobility had permanently changed the way artillery was deployed. Modern doctrines now emphasize shoot and scoot, tactics, ensuring that artillery can fire, relocate, and avoid detection. This fundamental shift in artillery usage is directly traceable to the innovations of World War II. One of the less visible, but equally important artillery innovations of World War II was the development of advanced fire control systems. In earlier conflicts, artillery fire often relied on rough calculations, spotters, and manual adjustments that could lead to delays and inaccuracies. However, the fast-moving nature of World War II battles required quicker, more precise targeting methods. Advances in mathematics, engineering, and communication technology enabled the creation of sophisticated fire direction centers, which coordinated the actions of multiple artillery batteries. Radios replaced slower field telephones, allowing for rapid adjustment of firing coordinates. Artillery officers developed detailed firing tables, taking into account wind, elevation, temperature, and ammunition type to improve accuracy. The use of forward observers, equipped with radios and sometimes even aircraft support, allowed artillery fire to be corrected in real time. These systems transformed artillery into a highly responsive battlefield tool, capable of striking enemy positions with remarkable accuracy. The integration of science and technology into fire control set the stage for post-war innovations, including digital computers and GPS-guided targeting, which would eventually give rise to precision-guided munitions. Another key component of improved fire control during World War II was the use of forward observers. Positioned on the front lines, in observation posts, or even flying in aircraft, forward observers acted as the yes of the artillery. Their job was to identify enemy positions, calculate range and direction, and relay corrections back to artillery units. This system greatly improved the accuracy and responsiveness of artillery fire, reducing wasted ammunition and maximizing battlefield impact. In the North African desert, for instance, British and American forward observers often worked closely with tank units to direct fire onto enemy strongholds. On the Eastern Front, Soviet observers relayed artillery fire against German positions, often under extremely dangerous conditions. The forward observer system made artillery more dynamic, allowing it to directly support advancing infantry and armor, rather than relying solely on pre-planned barrages. This innovation remains central to modern artillery doctrine, with forward observers now equipped with laser designators, drones, and digital targeting equipment. The principle, however, remains the same. Effective artillery requires real-time observation and coordination, a lesson first mastered during World War II. World War II also saw the dramatic introduction of rocket artillery, which brought both psychological terror and destructive firepower to the battlefield. Unlike traditional guns that fired shells, rocket artillery used multiple rocket launchers to unleash devastating barrages over wide areas. The most famous example was the Soviet Katyusha, nicknamed Stalin's organ, because of the terrifying noise it made when firing. German forces developed their own version, the Nebelwerfer, while the Allies experimented with systems like the American Calliope rocket launcher, mounted on Sherman tanks. Rocket artillery had several advantages. It could saturate a target area quickly, overwhelm defenses, and devastate enemy morale. Its drawbacks included limited range, reduced accuracy compared to conventional guns, and vulnerability to counter battery fire. Nevertheless, rocket artillery played a major role in major offensives, particularly on the Eastern Front, where Soviet Katyushas were used to crush German defensive lines. Although early rocket systems lacked precision, their sheer destructive capability paved the way for modern multiple-launch rocket systems, MLRs, which combine mobility with computer-guided accuracy. Today's advanced systems like AIM-RS and BM-30 Smerch owe their origins to these World War II-era innovations. Beyond its destructive power, rocket artillery had an enormous psychological impact on enemy troops. The loud, screeching sound of a Katyusha or Nebelwerfer barrage created panic long before the rockets even landed. Soldiers often described the experience as terrifying, with the noise and explosions shaking entire battlefields. This effect made rocket artillery as much a psychological weapon as a physical one. German soldiers on the Eastern Front dreaded Katyusha barrages, which often preceded massive Soviet offensives. Similarly, Allied troops facing German Nebelwerfers in Normandy found the noise almost unbearable, adding to the stress of combat. The unpredictability of rocket strikes also contributed to their fear factor. Since rockets were less accurate than shells and could land anywhere within a wide area. The psychological dimension of rocket artillery was so significant that military planners factored it into their strategies, using rocket barrages to weaken enemy morale before launching attacks. This concept of using firepower to break the enemies will remain relevant in modern warfare, where rocket and missile strikes are often designed to produce shock and awe alongside physical destruction. One of the most revolutionary artillery innovations of World War II was the proximity fuse, sometimes called the VT fuse. Before this development, artillery shells typically detonated on impact or after a timed delay. This limited their effectiveness against fast, moving aircraft or dispersed infantry. The proximity fuse solved this problem by using miniature radar systems inside the shell. When the shell came close to a target, the fuse automatically triggered detonation, maximizing destructive power. Developed primarily by American and British scientists, the proximity fuse proved devastating against enemy aircraft, especially Japanese kamikaze planes in the Pacific. It also transformed ground warfare, as shells could now explode above enemy troops, creating deadly airbursts. This greatly increased artillery lethality and reduced the need for pinpoint accuracy. Winston Churchill himself called the proximity fuse one of the most important inventions of the war, alongside radar and the atomic bomb. After the war, the technology was refined and became standard in modern munitions, setting the stage for smart fuses and guided artillery rounds. While proximity fuses improved artillery effectiveness against ground forces, their most dramatic impact was in air defense. Before their introduction, anti-aircraft guns had to rely on timed fuses, requiring precise calculations to predict where an aircraft would be at the moment of detonation. Even small errors meant wasted shots. The proximity fuse eliminated this problem by ensuring that shells exploded as soon as they came within lethal range of enemy aircraft. During naval battles in the Pacific, U.S. Navy ships equipped with proximity fused shells dramatically increased their kill rates against Japanese aircraft, particularly kamikazes. This development arguably saved countless lives and ships during critical battles like Leyte Gulf and Okinawa. The fuse's effectiveness was so great that it remained a closely guarded secret for much of the war, with restrictions on its use in certain theaters to prevent it from falling into enemy hands. Its success also paved the way for modern surface-to-air missiles, which use similar principles of proximity detonation. Thus, the proximity fuse not only changed artillery, but also revolutionized air defense technology. Another groundbreaking innovation during World War II was the use of radar in artillery targeting and detection. Radar technology, originally developed for early warning against aircraft, quickly found applications in directing artillery fire. Counter-battery radar systems could detect incoming enemy shells and trace their trajectory back to the point of origin, allowing friendly forces to fire back at enemy artillery positions with great accuracy. Additionally, radar was used to track aircraft and assist anti-aircraft batteries in aiming more effectively. This was particularly important during the defense of Britain, where radar-directed artillery helped repel German bombing raids. In the Pacific, radar-equipped ships combined this technology with proximity, fused shells, creating a highly effective defense network. Radar targeting also made night operations and poor weather engagements far more feasible, as artillery no longer relied solely on visual observation. These advances turned artillery into a far more precise and adaptable weapon. The integration of radar into artillery fire control marked the beginning of a technological trend that continues today, with modern artillery relying heavily on advanced sensors, GPS, and satellite guidance. One of the most direct battlefield applications of radar in World War II was in counter-battery fire. Traditionally, detecting enemy artillery required scouts, forward observers, or simply enduring incoming fire until the source could be guessed. This was both dangerous and inefficient. Radar solved the problem by detecting the trajectory of incoming shells, almost immediately after they were fired. Using mathematical calculations, artillery units could determine the exact location of enemy guns and return fire within minutes. This innovation drastically reduced the effectiveness of enemy artillery, forcing them to adopt shoot and scoot tactics to avoid retaliation. In the late stages of the war, Allied forces used radar-based counter-battery fire with devastating results, particularly during the campaigns in Western Europe. The system transformed artillery duels from a battle of endurance into a contest of speed and precision. Today, counter-battery radars such as the US AN/TPQ-53 or Russia's Zoopark-1 owe their lineage to these early wartime experiments. The idea that radar could neutralize enemy guns before they could inflict significant damage became one of the most lasting tactical revolutions in artillery warfare. Another critical innovation during World War II was the large-scale standardization of artillery pieces, ammunition, and logistical support. In World War I, armies often fielded a chaotic mix of calibers, designs, and ammunition types, which made supply lines a nightmare. By the 1940s, however, major powers realized that efficiency required uniformity. The US Army, for instance, heavily relied on the 105mm howitzer and the 155mm gun as its primary artillery systems, streamlining both production and logistics. Britain standardized its forces around the versatile 25-pounder, while the Soviets emphasized mass production of the 76.2mm and later the 122mm guns. This standardization meant that spare parts, ammunition, and training could be managed much more effectively, reducing confusion and waste on the battlefield. Moreover, standardized artillery allowed for large-scale, synchronized bombardments, as batteries could easily coordinate fire using common equipment. This logistical innovation may seem less dramatic than radar or rockets, but it had a profound effect on wartime efficiency and laid the foundation for modern military supply chains, where interoperability and standardization remain crucial principles. World War II was not just about technological innovations, but also about doctrinal shifts. One of the most important developments was the integration of artillery into combined arms operations. In earlier wars, artillery often operated independently, delivering pre-planned bombardments that were sometimes disconnected from infantry and armor movements. World War II changed this by emphasizing close coordination between different branches of the military. Artillery became an essential support tool for advancing tanks and infantry, providing suppressive fire to neutralize enemy defenses. German blitzkrieg tactics, Soviet deep battle strategies, and Allied combined arms assaults all relied heavily on artillery as a flexible tool, rather than a blunt instrument. Artillery fire was now called in dynamically by forward observers, coordinated with air strikes, and synchronized with armored breakthroughs. This doctrinal innovation ensured that artillery was no longer just a background weapon but a frontline enabler of maneuver warfare. The lessons of combined arms integration continue to shape military doctrine today, where artillery, air support, and mechanized units work together seamlessly in operations. While mobility and rapid fire support dominated much of World War II artillery development, there was still a place for heavy siege guns. The German army, in particular, fielded massive weapons like the 800 mm Schwerer Gustav and the 600 mm Karl Gerhardt mortar. These enormous guns were designed to destroy fortifications, such as those encountered in the Maginot Line or Soviet strongholds. Although their practicality was limited due to size, weight, and slow firing rates, these siege weapons demonstrated the extremes to which artillery innovation could be pushed. Heavy artillery was also used effectively in more practical forms, such as the Soviet 2003 BM howitzers or American 240 Nemiev guns, which provided devastating firepower against entrenched enemy positions. Even though post-war artillery focused more on mobility than sheer size, the psychological and tactical impact of these giant guns left a lasting impression. They reminded military planners that artillery could not only support mobile warfare but also serve as a decisive tool in breaking heavily fortified defenses when required. Another often overlooked aspect of artillery innovation in World War II was the role of mass production of industrial efficiency. The United States, in particular, demonstrated how industrial capacity could transform artillery warfare. Factories produced thousands of standardized howitzers, along with millions of rounds of ammunition, ensuring that frontline units were never short of firepower. This industrial advantage meant that US and Allied artillery could often outgun the Axis, not only in quality, but in sheer quantity. The Soviet Union applied a similar philosophy, focusing on simple, rugged designs like the 76.2 mm's divisional gun, which could be produced in massive numbers and deployed across the vast Eastern Front. By contrast, Germany's focus on specialized or overly complex designs sometimes limited its artillery output, despite impressive engineering achievements. This lesson, that simple, standardized, and mass-produced artillery could often outperform complex but scarce weapons, became a cornerstone of modern military, industrial planning. The ability to maintain consistent artillery supply and deployment was as decisive as any battlefield tactic. Artillery innovations during World War II were not confined to land. Naval artillery also saw significant advancements that influenced both sea and land operations. Battleships and cruisers, equipped with massive guns, were used extensively for shore bombardment, supporting amphibious operations such as the day landings in Normandy and the island, hopping campaigns in the Pacific. Innovations in naval gunnery, including radar fire control and improved spotting techniques, made these bombardments far more accurate than in previous wars. The ability of naval artillery to deliver sustained, heavy firepower onto coastal defences gave invading forces a crucial advantage. Furthermore, the integration of naval gunfire with land-based operations represented another step forward in combined arms warfare. Naval artillery also influenced post-war missile development, as many of the principles of long-range gunnery were adapted into rocket and missile systems. While aircraft carriers eventually eclipsed battleships in importance, the innovations in naval artillery during World War II ensured that big guns remained a formidable tool for both sea and land operations. Artillery effectiveness in World War II was also enhanced by significant improvements in ammunition. Beyond the introduction of the proximity fuse, new shell types were developed to meet specific tactical needs. High, explosive shells became standard for general bombardment, while armor-piercing shells were designed to penetrate tanks and fortifications. Smoke shells provided concealment or signaling, while incendiary shells set fire to enemy positions and supplies. Chemical shells were stockpiled but rarely used due to international conventions, though their existence influenced strategic planning. Specialized ammunition expanded the tactical flexibility of artillery, making it useful in a wider variety of battlefield roles. For instance, the German Nebelwerfer could fire both explosive and smoke rockets, while Allied artillery used white phosphorus rounds for both smoke cover and anti-personnel effects. These innovations demonstrated that artillery was not just about firing bigger shells, but about tailoring firepower to the specific requirements of combat. The legacy of specialized ammunition lives on in modern artillery, which now employs guided shells, cluster munitions, and other advanced warheads. World War II also demonstrated the crucial role of artillery in urban combat, where fighting often took place street by street and building by building. Cities such as Stalingrad, Warsaw, and Berlin became brutal testing grounds for artillery's adaptability. Traditional long-range bombardments often caused massive destruction but could also hinder advancing forces by turning cities into rubble-strewn obstacles. To address this, armies developed new techniques for integrating artillery into close support roles. Smaller, caliber artillery pieces were used for direct fire against fortified buildings, while larger guns were employed to collapse enemy strongholds. Mortars became especially valuable in urban combat, providing flexible and immediate firepower in confined spaces. The use of artillery in urban warfare highlighted both its strengths and limitations. While it could devastate enemy defences, it also risked high civilian casualties and destruction of infrastructure. These lessons have shaped modern doctrines for artillery use in cities, emphasizing precision, coordination, and restraint to balance military effectiveness with humanitarian concerns. By the end of World War II, artillery had been transformed from a relatively static support weapon into a highly mobile, versatile, and technologically advanced arm of warfare. The combination of self-propelled artillery, advanced fire control rocket systems, proximity fuses, and radar targeting laid the groundwork for post-war developments. During the Cold War, these innovations evolved into even more sophisticated systems, including nuclear-capable artillery, computer-guided fire control, and highly mobile multiple rocket launchers. Many of today's most advanced artillery systems can trace their design philosophy Back to World War II innovations. Just as importantly, the doctrinal lessons of combined arms operations and dynamic artillery support remain central to modern military strategy. The war demonstrated that artillery was not simply a background weapon, but a decisive force multiplier, capable of shaping battles and campaigns. These lessons ensured that artillery continued to be heavily funded, researched, and integrated into the modern battlefield. The 5 major innovations of World War II: self-propelled artillery, advanced fire control, rocket artillery, proximity fuses, and radar targeting, did more than improve battlefield effectiveness. They fundamentally redefined the role of artillery in modern warfare. No longer a static instrument of attrition, artillery became a dynamic tool of precision, mobility, and overwhelming firepower. The psychological impact of rocket barrages, the devastating efficiency of proximity fuses, and the pinpoint accuracy provided by radar and forward observers transformed how commanders viewed artillery. These innovations also influenced post-war military technology, from guided missiles to digital targeting systems. More than 80 years later, the principles established during World War II still shape artillery design and doctrine. Modern armies around the world rely on systems that are direct descendants of wartime innovations, proving that the Second World War was truly a turning point in artillery history. As technology continues to advance, from GPS, guided shells to autonomous drone integration, the legacy of World War II innovations reminds us that artillery remains the king of battle. Forever changed by the fires of the world's most devastating conflict.